Today I'll be talking about large-scale structure and measurements of large-scale structure using a relatively new technique, 21 centimeter intensity mapping, and what we can learn about cosmology from those measurements. So Brian Greene said this somewhat dramatically, but noted that we as humans are storytellers, and what could be more grand than the story of creation. So certainly many people could take issue with this and say that particular branches of science are more interesting than cosmology, but cosmologists definitely have an interesting story to tell. So we know the universe started off with a Big Bang about 14 billion years ago. We believe it went through a period of rapid expansion which we call inflation, where it expanded over 25 orders of magnitude in the space of much less than a second. After that, the universe expanded at a more lackadaisical rate, eventually forming neutral hydrogen and then releasing the cosmic microwave background, which we of course measure again today. After that, the universe was largely neutral hydrogen until the first stars, galaxies, et cetera, black holes began to form. That ionized that neutral hydrogen and made it all go away. And then the structure formation of the universe continued over the next 13 or so billion years, forming clusters of galaxies and larger structure over time. Finally, about maybe 4 billion years ago or so, the expansion rate of the universe began to accelerate, something which we attribute to dark energy. So from this figure, you would think that we had figured it all out. We basically knew everything about the universe, and we can all go home and stop worrying about it. But of course, if you take a cosmologist out for beer and ask us a few more questions about this, you might get a different answer. We would say that this period of rapid expansion that we call inflation, there's no unique evidence right now to support that theory. So we can't say definitively that this inflation actually happened. This period when the universe was largely neutral hydrogen and the first objects began to form, we know very little about that period, what those objects were, and how that proceeded. We don't know what those first objects were, so these first stars, we're not sure what they are. Most astronomers will tell you this stuff, the development in galaxies and planets, is also a pretty big question mark, so we don't know a lot about that either. There's a lot of room for learning new things. And then finally, this period of rapid expansion, this period of expansion that started to accelerate about 4 billion years ago, we don't really know the underlying cause of that either. So there's actually many holes in our knowledge in this picture. So I am an experimentalist, so of course I am interested in what we can measure to help us answer some of these questions. I'm going to focus largely on this last question in this talk, what we can learn about dark energy in our current accelerated expansion of the universe through different measurements. So one set of measurements that I'm not going to have a chance to talk about are measurements of the cosmic microwave background with 2 experiments, Simon's Observatory and CMB stage 4. I will mostly be focusing on what we can learn about the expansion of the universe through measurements of large-scale structure, so through the distribution of galaxies across cosmic time. And specifically with the 21 centimeter experiments, CHIME and HIRAX. So I made these 2 things sound very separate. So we have the cosmic microwave background that was formed about 400,000 years after the Big Bang. We see it today as a radiation pattern, and we measure it with all of our wonderful CMB telescopes. And then there's also the distribution of galaxies in the sky from more recent measurements and galaxy surveys. It turns out there's a fundamental scale that lives in both of those signatures. So if you measure the CMB and find, say, all of the hot spots or all of the cold spots and stack them on top of each other, you'll end up with a sort of ring-like feature around a given hotspot or around a sum of hotspots and cold spots. You'd find the same thing in a galaxy survey as well. And that's not a coincidence. So that there's a fundamental scale that lives in both of those signals. That is what we're going to exploit to understand the expansion history of the universe. For cosmologists, this is not a surprise. They already know about this, but for other people, this might sound a little weird. Some signal that was made 400,000 years after the Big Bang somehow magically shows up again in the distribution of galaxies in the sky today. So how did that work? So it's pretty straightforward, but we have to cast our minds back to about 400,000 years after the Big Bang to understand where it came from. So back then, the universe didn't have stars, didn't have galaxies. It was just a coupled photon baryon fluid. It was basically just constituent particles that were coupled together through Thomson scattering. So we are going to, and in that universe, there were small overdense regions scattered throughout the universe. These overdense regions would seed pressure waves that would propagate out through this coupled fluid. And so we're going to watch one of these pressure waves propagate through this coupled fluid. And specifically, we're going to watch it in baryons. So largely, you should view this as electrons and in photons. So we're going to watch it in physical space on the two left-hand panels. And then you can also do sort of a radial profile if you just picked the center and then summed in annuli around it, sort of how many baryons and how many photons do you get. So that's the radial profile on the right-hand side. So we're going to start universe less than 400,000 years old. A pressure wave just began to propagate outwards from its little central region. And we can see that the baryons and the photons look the same. And we can check that in this radial profile. And that's because, of course, this fluid is coupled together. So you would expect these two types of particles to look the same. So we're going to watch this pressure wave propagate outwards from its little central overdense region. So sometime later, but the universe is still less than 400,000 years old. The pressure wave has propagated outwards a little bit. The baryons and photons are still coupled together. So these two pictures look identical. And again, we can check that in the radial profile, looks the same. So we expect that. And then something interesting happened when the universe was about 400,000 years old. So at this point, the universe had expanded and cooled just enough to start forming neutral hydrogen that decoupled the photons from the electrons. And so now this pressure wave looks like the other pressure wave from earlier in baryon density, but the photons are starting to sort of free stream away from this pressure wave system. And you can see that in the radial profile as the baryons are beginning to, the photons are beginning to sort of move away from this pressure wave. That gets worse as time goes on and the photons free stream even more away. But the baryons are sort of, in some sense, captured. This pressure wave stalls because it's no longer supported by those photons. So it just kind of hangs out there until those baryons begin falling back towards the central overdense region that they started from. So again, there's still an overdensity there. So some of the baryons are gonna start to collect back in the middle. So you can see that in the radial profile where the photons are sort of free streamed away. They're almost non-existent at this point in density, but some baryons are starting to fall back again to the center. And then we can go all the way to today. The photons are gone. We'll measure them again as the cosmic microwave background. But the baryons have ended up in basically two places. One is back at the center where they started, but there's a sort of remnant ring-like feature that has stayed in place from this initial pressure wave that started when the universe was younger. So we end up with a sort of remnant overdensity of baryons in the place where the pressure wave stalled. So we get a collection of more baryons in these two regions, and that means ultimately a collection of more galaxies in these regions. So we would preferentially find galaxies at the center where there's more baryons, and then again in a ring, sort of ring-like feature around that central place. So we'll end up with more galaxies in these, again, in the center and in a ring around that center. You don't have to believe me, this has been measured. So of course, this is a statistical statement, so we can't actually find rings in the sky, but we can look for them statistically using galaxy surveys. So this is a galaxy survey, Sloan Digital Sky Survey. This picture on the left represents 300,000 galaxies that traces basically where all of the galaxies were out to redshifts of about 0.14 or so. So to look for these ring-like features, you basically find every galaxy in the map and then ask how many galaxies are some distance away, some in rings around your favorite galaxy, and then do that for every single galaxy in this survey. So what you find is on the right-hand side in this plot. So what you build up from doing that is what they call a correlation function, but this basically looks for, basically how many galaxies are some particular distance away from another galaxy. And you find that there's a bump at about 100 H inverse megaparsecs or so. That bump is a remnant of that ring-like feature. So this bump right here is exactly the thing that we found from our little toy model on the previous slide. So this is a 7 or so sigma result. There are even more impressive ones, of course, now from more recent surveys. But this is showing the same sort of thing that the previous slide did, which is that there's extra power at a given scale away from the at a given scale. We find the same thing in the CMB, of course. So you can do nearly the same thing, stack up hot spots and cold spots, and then look for how much power is some given distance away, and you'll find again this ring-like feature in the CMB as well. So this gives us a powerful probe. We have a measurement from the CMB that gives us a scale that was set when the universe was about 400,000 years old and the CMB was formed. That same scale we will measure again in the galaxy distributions on the sky. This ring-like feature expands with the universe for the galaxies, and so we can use this to understand how the universe has expanded over time between the CMB and whenever you were measuring those galaxies. So this is a special enough type of measurement that we give it a name. So these are baryon acoustic oscillations. So if I say BAO, you should just think ring-like feature left over in the galaxy distribution. So we now have a technique for trying to understand how the universe has expanded over time, but what do we actually want to measure and how do we use this to, say, constrain something about dark energy, which of course we only see by its influence over the expansion history of the universe. So, this seems like a really excellent way to measure dark energy, but what parameters do we actually want to measure when we say measure dark energy? So usually we're talking about measuring the equation of state. So the equation of state relates the pressure of a given fluid or object to its density. We'll make it linear. So we just put a W in front, and then that W becomes our equation of state parameter. We can use a combination of basically general relativity and our favorite cosmology metric to write down how the density of a given constituent changes as the universe expands. So that's given here with this equation. And how that depends on W, this equation of state parameter. Here, A is what we call the scale factor. So this just encodes cosmic size. It's 1 today and was smaller in the past. So we've just kind of normalized it to be 1 today so that we don't have to deal with actual units. So we can get a few examples for what these for what equation of state means for different things that at least we know about. So for example, matter has an equation of state of 0-ish. So if we put 0 into this equation, we'll find that the energy density of matter goes down like a to the -3, or goes down like volume. So that makes sense. If you have matter and the universe expands, you'd expect that its density would go down like volume. Radiation has an equation of state of 1/3. This turns out to mean that its energy density goes down like a to the -4. So it's kind of like going down like volume with an extra factor of, say, wavelength, because it's the energy density, not just the density of the photons. We can also put in another number. We'll put in another number. We could estimate a W of -1, for example. So I can do this math. If I put a -1 in this equation, I'll get a constant energy density. So that's the rough equivalent of, say, having a particle in a box, doubling the size of the box, and then doubling the volume of the box, and then suddenly getting 2 particles out. So this would be something that you might associate with how much volume of space you have, and certainly is weird and doesn't behave really anything like matter. There's an extra implication for this, which is, of course, as the universe expands, the energy density of matter and radiation decreases, but something that has a constant energy density may eventually take over the total energy density of the universe, simply because it's constant. So you just draw a straight line basically here. So thank God we don't have anything like that in the universe, except that it turns out we do. So dark energy currently seems like the constraints show that dark energy is equivalent to roughly a constant. So its equation of state is about -1. And we are in the scenario where it has taken over the total energy density of the universe. So about 72% of our universe is made up of dark energy, and the rest of it is dark matter and regular matter. So we're dominated by dark energy, and it has obviously kind of a strange behavior. It dominates the universe, and we don't really have any great models for it. If you ask particle physicists, they would tell you that vacuum energy is a thing that exists, so energy associated with space itself. But their estimates for how much of it you should have are about 120 orders of magnitude larger than the actual measured value of dark energy today. So that's not a great prediction, basically, for what we measure. So we still end up with a fundamental mystery of what is this stuff that's dominating our energy content. So the best constraint so far is that the equation of state is consistent with -1, with about 7 or so percent error bars on it. So you can actually imagine that maybe you could have some room for non-constant dark energy models. So they might be weird, but there is wiggle room for adding in perhaps models that end up sounding more fundamental than simply sticking a constant into GR. In addition, as many of you in the audience may know, there is a tension in lambda CDM right now for the prediction of our local expansion rate, which we call H0. So the prediction from the CMB versus actual measurements from things like supernova that show this discrepancy at fairly high sigma between the predictions of the CMB and these more local measurements. And so The origin of this is right now unclear, but this is one of the few tensions in lambda CDM that we've really come across in recent history. So certainly deserves thought and consideration. So great. So I'll go back to this. So what you'd like to do is to understand whether the equation of state of dark energy is actually a constant or maybe something different. One thing that you can do, and the only thing that we really have access to on the measurement side, is to measure the expansion rate of the universe as a function of time. So basically walk back on our line back in time and ask how much had the universe expanded at different times in the past, and see if this it's consistent with a constant or something different. And that would tell you what sorts of models you may be trying to think about for what dark energy can fundamentally be. So measurements like baryon acoustic oscillation should be really good for this, because you can measure galaxies at lots of different redshifts. That should give you a scale at different redshifts or different points in time that allow you to understand how the universe has expanded over time. And so we're not the only people to think of this. Galaxy survey people really are interested in this question. And so we can ask, how well have baryon acoustic oscillations already constrained our cosmological models to be, and for example, how well have they constrained the dark energy equation of state to be something consistent with a constant? So here, I'm plotting measurements as a function of redshift. So time goes backwards, 0 is today, 2.5 is in the past. I've normalized some stuff. The main thing you should take away is if dark energy is constant, you would measure numbers that are on this flat line. So each of these gray points is a galaxy survey from fairly recent data. So you can see that they are certainly consistent with a line, but that the error bars are fairly large. So you can pretty easily allow some forms of some models that are not simply a constant, not simply on a line here. So what we would like are measurements that sort of fill in all these redshift ranges where we don't really have a lot of measurements, and then have tiny little error bars so that we can figure out if we're actually on this line or if the universe was doing something a little bit different. So that's what we'd like. So how do we get it? Baryon acoustic oscillations, again, seem like a good way to do this. They can be measured out to high redshift. You can measure galaxies out to high redshift. So we have a couple options. One is do what we did before. So take a really big optical survey, make it even better, find even more galaxies, look even further in the past, and try to do a really good job of getting those error bars down and filling in these redshift ranges. So you can do that, and certainly optical surveys are doing that even now. But we can also think of a different way of making these measurements. So these baryon acoustic oscillation features are large. They're about 150 megaparsecs in radius. So they contain hundreds of thousands or millions of galaxies. So I can imagine, if I drew my baryon acoustic oscillation feature on this SDSS map, it might be roughly like this bullseye shape. So I could imagine taking that SDSS survey and just blurring it out a little bit. So such that I can still pick out this baryon acoustic oscillation feature, but maybe I didn't measure every individual galaxy. Maybe I averaged a bunch of galaxies together. So we don't need to resolve individual galaxies to measure this BAO feature, this BAO peak. What we do need is something that traces the dark matter distribution, so the same underlying thing that galaxies trace, and also gives us redshift information so we can figure out where we made that measurement in time to chart out the whole history of the expansion rate. It turns out neutral hydrogen is a really great way to do this. So neutral hydrogen gives off 21 centimeter photons when the electron goes from spin aligned with the proton to spin anti-aligned with the proton. Neutral hydrogen is also extremely abundant. So this is a picture of a galaxy in ionized hydrogen and then in neutral hydrogen. You can see there's a bunch of neutral hydrogen. It's really bright. So there's a 21 centimeter radio measurement of this galaxy. Neutral hydrogen is abundant in these galaxies. And so can be used as a tracer in the same way that we use optical surveys for tracing where the galaxies are. So if I wanted to build an experiment that was going to measure galaxies at high redshift, but using their neutral hydrogen emission instead of their optical emission, let's say I was interested in redshifts between, say, 0.8 and 2.5. So a redshift, a 21 centimeter photon that was emitted at redshift 2.5, the wavelength of that light would have expanded over time. And today we would measure that as a 75 centimeter photon instead, or 400 megahertz. If a galaxy emitted a 21 centimeter photon at a redshift of 0.8, would have that photon would also have had its wavelength expanded as it redshifted, but wouldn't be quite as big. So we'd have a, say, 38 centimeter photon or so from a redshift of 0.8, or a measurement at 800 megahertz in frequency. So if we wanted to measure 21 centimeter emission between a redshift range of 0.8 and 2.5, we would build an experiment that operated between 400 to 800 megahertz. There has been a detection of 21 centimeter emission in high redshift galaxies through cross correlation. So a measurement from the radio telescope Green Bank telescope in cross correlation with, in this case, EBOS and Wiggle-Z, yielded an estimate for the amount of neutral hydrogen that lived in those galaxies. So what's shown here are, so that's shown as these black points at a redshift of about 0.8 or so. And you can see it's consistent. These dark points are consistent with the purple points, so known from presumably Lyman alpha measurements, and show that these galaxies certainly contain neutral hydrogen, and even well enough to constrain how much neutral hydrogen lived in them. So there is hope. Galaxies at these redshifts certainly contain neutral hydrogen. We can at least measure it through cross correlations right now to verify that. And so this is evidence that, high redshift galaxies contain neutral hydrogen. And so you should be able to use 21 centimeter emission as a galaxy probe. So we built an experiment to go to measure dark energy in these redshift ranges using the 21 centimeter emission from neutral hydrogen. So this is CHIME, the Canadian Hydrogen Intensity Mapping Experiment. It is a collaboration of bunches of people with 4 main institutions in Canada. It consists of 4 cylinders, which are each 20 meters wide, so 20 meters in the sort of curved direction by 100 meters long. So that gives us an 80 meter by 100 meter telescope. On this telescope, we have over 1,000 dual polarization feeds. So that's over 2,000 channels, since dual polarization means 2 polarizations. We operate between 400 and 800 megahertz. That gives us our redshift range of 0.8 to 2.5. And we've been taking data for about 3 years or so now, 3.5 years. So we had our first light ceremony September 7th, 2017. And for scale, this is the Canadian Minister of Science back in 2017. So you can see that this telescope is really quite large. Here's one of the beams, one of the curved beams for it. I will briefly go through the instrument itself. We, as is true for basically every telescope, there is a curved reflector. In our case, that's a cylindrical reflector. the light is focused up to a line that goes along those cylinders. So you can see for scale about how big that focal line is. It can hold people. The signals are picked up by these radio feeds, these antennas. That signal is amplified by a set of low noise amplifiers and then sent over a bunch of coaxial cable to all of our digital electronics that live in RFI enclosed shipping containers. So the presence of shipping containers is always how you know this is a cosmology experiment. So the data from these 1024 feeds is digitized and channelized into 1,000 frequencies. So now for every input, we have 1,000 numbers in a 400, 800 megahertz frequency range. That turns out to be a lot of data, 6.6 terabits per second total. So if I was going to store the data directly coming off of our digitized back end, if I were trying to store this on my laptop, I'd be able to get, my laptop's not that powerful, but I'd be able to keep it for about half a second and then my laptop would be full. So luckily that's not our plan for storing our data. After that, the data gets sent to two 40-foot shipping containers filled with GPUs. These do what's known as the cross correlation. So they take, for every one of these 1,000 frequencies, they take signals from every pair of feeds and multiply them by each other. So this is a radio version of resolution. I'll talk about this a little bit more in a second. These shipping containers filled with GPUs are impressive, I have to say. We also had to move to water cooling to be able to handle the amount of raw power in heat that these things are dumping out into the world. So a lot of engineering actually had to go into building this back end for CHIME, and it was probably more work than all of the, reflector, feed, LNA stuff combined. So at the end of the day, CHIME is a transit telescope. There we go. It's far too big to move, so it just sits there on the ground and we let the sky rotate overhead. So it's a transit telescope. That allows us to see the entire sky every day. So we get to make a map of the sky each day. It's located in Penticton, British Columbia, which is about 5 hours inland of Vancouver. So it's in the coastal mountain range. CHIME is an interferometer. The reason we have that complicated back end is to give us resolution on the sky. So if I did a really stupid thing and just put one single radio antenna on one single CHIME feed, one single CHIME reflector, the beam on the sky would be a big hot dog. So it would have no resolution in the north-south direction along the cylinder. But it would have a little bit of resolution in the east-west direction where it's curved. So I would end up with sort of a big, long hot dog shape on the sky above my telescope. Of course, that's not what we do. So we have a bunch of feeds. If I had, say, 7 feeds or 8 feeds on this radio dish, when I multiply each of these pairs of feeds together, I end up with additional resolution along the north-south direction. So this is a magical, not magical, but this is an interferometric technique to gain resolution by correlating signals together from radio dishes. So I would end up being able to have some resolution along my hot dog shape of my beam. And then if I added the rest of the cylinders, because I'm correlating each of the input pairs, in each of the inputs in pairs, I can do the same, I get the same math out where I get some additional resolution along the east-west direction from being able to combine pairs between these different cylinders. So I end up with basically a set of beams that live inside of my primary hot dog shaped beam. These allow me to have finer resolution on the sky using these interferometric techniques in pairs of feeds, by combining pairs of feeds. So this is how CHIME gets resolution on the sky and is able to actually make maps of the sky using our interferometer. So how well do we think we can do? So again, this is the state of the art from current baryon acoustic oscillation surveys. If we add our expectations from CHIME, the projections from CHIME alone are shown in red. So you can see maybe that we fill out this redshift range between 0.8 and 2.5. Again, that's because, of course, our frequency range has been chosen to fill out that redshift range. And you can see that our error bars are far smaller than the current surveys. And are even commensurate in the low redshift ranges with upcoming optical experiments such as DESI, and then far better at high redshift and beyond where they don't have any sensitivity. This assumes a 5-year survey for CHIME. And of course, we've been taking data now for about 3.5 years. So we're coming up on that 5-year survey mark. We make maps of the sky every day. We also combine those maps. So this is a map from 2 months of data from CHIME at one of our 1,000 frequency bins. So you can see a couple of things about this. One is this is the galaxy sort of falling on one side and rising on the next. There's a fan region of synchrotron emission in the northern part of our galaxy, and there are tons of little point sources all over this map. So we can make maps of the sky. We certainly measure a reasonable radio sky from this. So this is what you would expect from CHIME. Oh yeah,
are the horizontal stripes, are those side lobes excited by the galaxy, or are they like a pickup from like stuff on the ground?
Yeah, this is actually crosstalk that we weren't able to fully mitigate for this map. Yeah, so there's crosstalk between feeds along a cylinder and between feeds even across cylinders. And so there are, so you end up with these sort of horizontal stripy features basically running along the north-south part of our beam because of that. So that's because we haven't fully modeled crosstalk away yet. Yeah.
Okay, and you have 18 times more data than this, right?
We have 1,000 times more frequency bins, and then 3 years of data. Yeah. I don't know if that's 18 times, but yeah.
Yeah, okay.
Yeah. We have a lot more data than this. Yeah.
Yeah, I was just looking at the time, not the number.
Oh yeah, the time. Yeah, that's right.
Yeah.
Oh, and I should have re-highlighted this. So we make a map that doesn't look quite like this. It's not quite as nice as this, but we make one of these maps every night due to the cylindrical shape of our dishes. So we get a map like this every single day. We use that for calibrating the instrument and many other things based on the sources that are in this map. So we have science results from CHIME. We've been on the sky for over 3 years. Those science results are primarily, or right now only, from our fast radio burst analysis backend. So I'm going to highlight just a couple of these papers to talk about. Sorry, that's my dog. One is a second source of repeating fast radio bursts. So fast radio bursts are what they sound like, radio bursts that go off in the sky, and they're very fast, usually occurring over the course of a millisecond or a few. Not much is known about them, but less was known about them when CHIME existed. There had been one repeating burst that had been detected before this. CHIME found a second one, indicating that there were probably varieties of populations of fast radio bursts, but also indicating that at least one type of fast radio burst couldn't be a cataclysmic, the result of a cataclysmic explosion because it repeated. So we found a second one. We also were able to link one fast radio burst back to a galactic magnetar, which shows that perhaps at least one source of FRBs could be magnetars in other galaxies and our own. So that was a fun result too.
Laura, about 10 minutes left.
Oh no. Okay. Good. Okay. So one thing about this map does not show little tiny galaxies that are very far away. It only shows our galaxy. That is one of our biggest problems, being able to remove the galaxy from our maps, see through it so that we can make a cosmological detection of galaxies at high redshift. So I'm going to skip most of this. The hope, of course, is that the emission from our own galaxy is smooth across our frequency band, whereas our signal is not, because it's uncorrelated galaxies at a lot of different redshifts. And so we should be able to use the frequency, the fact that these don't have the same frequency dependence, to remove the smooth frequency emission and only detect the galaxies behind it. In order to do that, we have to calibrate our instrument extremely well. So I'm going to just talk about a couple of ways that we're doing this. So one is we have to understand basically how much amplification our instrument has every day. And so we have to understand what that's called the gain. So we have to understand our gain quite well. If we make a map of the sky every day and detect how bright a couple of different point sources are in that map, and just watch how that number changes over time, we can get a sense of how much our amplification is changing with time. So that's what's shown here in this plot, which Seth Siegel made. So across our frequency range, you're seeing basically in percent how much the brightness of our point sources is changing in the map over time, over 256 days, in fact. So if you just took a raw number from that, you would get the blue line. So you can see that this number would fluctuate from about 1 to 2% over the course of these 200 or so measurements. That's not good enough. We need to do better than 1% at least. So once we have removed the effects of thermal variation, so most of this variation in the 1 to 2% is actually coming from temperature changes over the course of a day and over the course of the year, et cetera. So we can correct for that because it's very consistent. So once you've done that correction, you end up with this green line at the bottom, which sort of hovers around a mean of about 0.75% or so, which is close to our actual goal of 0.7% in amplitude. So we are, just from the raw data alone, plus the thermal corrections, we're actually able to get very close already to our goal for knowing our gain over time, well enough to get cosmology out. Our second problem is beams. So I showed you our hot dog shaped beam on the sky. We have to understand either our synthesized beam or that hot dog shaped beam very well to be able to remove the foreground power that can leak in if we don't know it well. We have a few different handles on how we might be able to constrain the beam shape. So the different measurements we have are, again, point source measurements. So if you just take the map, the same map that I showed from CHIME data, ask how bright are all these different point sources, you can map out basically a bit of your north-south beam just from our knowledge of how bright they should be. So that gives you a crosswise selection through our north-south beam through the hot dog shape. We can use measurements from the sun. So the sun is one of the few sources that's extremely bright and actually moves from north to south during the year. So we can use solar data as well to map out our beam shape. And then finally, another technique that I'll talk about in a second. So our first technique is just using these point sources. So if we measure how bright all the point sources are and then divide them by how bright other telescopes have measured them to be, we can trace out the shape of our beam along this north-south hot dog. So that's shown in blue as these data points. We can actually fit a model that's fairly simple. It's based just on if you have a hot dog shaped beam and then a coupled hot dog shaped beam from an adjacent feed, with some time delay, what do you expect your shape along this north-south direction to be? And you can, turns out you can fit a model. It's actually pretty good. It goes through the data points very nicely. A couple things about this. One is our beam is not smooth. So you'll notice this coupling model has a bunch of ripples in it, which are measured in the point sources and expected in the model. So it doesn't look as beautiful as this hot dog shape that I'm showing on the left-hand side. But that structure is well captured by actually a fairly straightforward model for this. In addition, there's a frequency dependence. So if we measure at 692 megahertz, there's like a dip in the middle of our beam. So somewhere right around 0, there's like a decrement in our hot dog shape. But if you look at a different frequency, you get a bump instead. That's also predicted by this coupling model and well fit by this data. And this is all work by Saurabh Singh. That gives us some handle on our north-south beam, but unfortunately, CHIME alone is not good at measuring point sources because its beam is so big that we can't measure the flux from those point sources anywhere other than sort of right overhead. So if you're interested in the diffraction side lobes and things that show up at less than 10% of our beam, which we are interested in, you have to figure out a different way. So these are good for measuring the north-south slice, but are not good for measuring, say, an east-west slice, so the orthogonal direction. So one technique to get a handle on that is a measurement we make called holography. So there's a nearby dish right next to CHIME that can steer. I instrumented it with a 400 to 800 megahertz feed and amplifier set. That signal gets sent over into the CHIME correlator, and that allows us to correlate only what's common between CHIME and this little steerable dish. So we can boost our signal to noise on any given radio source that we're looking at with that steerable dish. So that gives us really excellent measurements in the east-west direction as the source transits. So this is a holography measurement of Cygnus A, one of the brightest radio sources in our sky. And you can see you get a nice measurement of the main beam shape, and then these diffraction side lobes out on the side out to plus and minus 15 degrees and even further than that. There's a lot of extra data in here that I'm not going into, but there's things like the cross polarization and the phase can also be measured using this technique. And these measurements are my graduate student Alex and a UBC graduate student Tristan. I'll skip that. In addition, so you can do that for many sources. In addition, there's one other measurement that can give you that gives you actually both north-south along the hot dog and east-west across the hot dog beam measurements, and that's the sun. So the sun moves from 47 degrees north to south over the course of a year and is super bright. So we can actually pick it up outside of the main beam shape for CHIME. So this is work by Dallas Wolf and shows the complications involved in the CHIME beam shape. So we have all of these diffraction side lobes as you cut slices along the hot dog, in addition to a lot of fun structure in the north-south direction as well. So this has been a really fruitful way to build models for our beam shape. Work by Gary Hinshaw and others in particular. And then finally, CHIME has access to basically the entire northern sky from its location in Canada. But there's a southern part of the sky that has a lot of cosmological surveys, upcoming cosmological surveys in it. So to take advantage of that and the much more radio quiet area available in South Africa, we are building HIRAX, the Hydrogen Intensity and Real-Time Analysis Experiment. So it will operate in the same frequency range as CHIME, 400, 800 megahertz. So that gives us the redshift range of 0.8 to 2.5. We'll deploy dishes instead of cylinders, so an array of 1,024 circular dishes. And it will go in the Karoo Desert in South Africa, basically right next to the Square Kilometer Array telescope, which means that we'll be very protected from radio frequency interference over the course of the next few decades, basically by hanging out right next to SKA. We have a prototype array of 8 dishes that are not at the SKA site, but are outside of Johannesburg, where there's a bunch of RFI. But that's been a fun test bed for the different technologies that we've been testing for HIRAX. So I started this talk noting that I was going to focus on how to better quantify and understand the accelerated expansion of the history over time and what we might learn about dark energy from that. But of course, a measurement of large-scale structure gives you a lot of other interesting cosmological measurements. So we can measure isotropy, we can measure non-Gaussianity. This can give you some estimate of the sum of the neutrino masses, and then potentially distinguish between, say, modified GR models and dark energy, among other things. So I'm going to leave it there, and that gives you a handle, of course, on all these other fun science goals that we're interested about in cosmology. So I'm going to leave it there, but just have a teaser in case you want to ask me anything about some of my more experimental work and not just CHIME analysis.
Thank you, Laura.
Mm-hmm.
Yes, let's virtually clap hands. Or not virtually. If you have any question, please raise your hand. It'll be just a bit easier to handle. Sigurd.
Yeah. How much of this beam complexity comes due to having this hybrid between interferometry and normal focusing? Like if you just had an array of normal dishes, would the beam be a lot easier in that case?
I sure hope so, yeah. I think much of our beam complexity does come from all of this coupling structure. So the fact that even the primary, what you might consider the primary beam from a single feed has to get modified by the fact that it can pick up signals from an adjacent feed and even from a few feeds down. So the coupling models that Gary has put together and that Saurav's been estimating show we have about 15% coupling with the feed right next door, about 3% coupling to the one, the one after that, and then after that it's pretty negligible. But that means there's there's a significant amount of power that we have to be able to model and understand to remove from the beam shape. So the hope would be that with circular dishes that are isolated from each other, you don't have to have as much of that coupling, and you can at least not have those effects. There are going to be other beam effects. You can't get away from those, but at least the coupling part, I think, being able to physically isolate feeds from each other could make it easier. That said, Gary's models are pretty good. You know, like it's we're like not at the 0.1% level yet, but the residuals are getting down to more like 3% or so. So it seems like it's getting handleable.
Okay.
Yeah.
Alberto?
Hey, Laura, so how much of a concern are the satellite constellations that are being deployed all the time?
Yeah. From the radio side, not too bad so far. Our bigger problem is, so in CHIME, Canada has auctioned off the 400, 800 megahertz band to cell phone companies. So we have actually seen over the course of even the last year, parts of our radio band start getting just, you know, removed from RFI. So it's getting worse all the time. So far that I would say that's still our biggest concern, certainly on the CHIME side. There are ways we could probably handle that through more clever RFI, you know, real-time RFI removal. That's had to be done very well by experiments like LOFAR that operate in way more RFI contaminated areas than we're in. So that's, you know, that's a possibility, but it wasn't something we built directly into the processing. So I, you know, I'm not trying to say like CHIME can't exist 2 years from now, but you know, doing more cosmology with CHIME 10 years from now will probably require more thought. My impression so far is that the satellite constellations are still a bigger problem for the optical telescopes, but you know, no one really cares about radio astronomy. So someday that statement will probably not be true anymore. Yeah.
Thank you.
Yeah.
Sigurd has another question.
Yeah, I wondered if, so it sounds like these half pipes being close to each other is part of the problem why you get a complicated beam. So would it be easier if they were further away from each other and maybe at different angles to each other?
That's an interesting question. Further away would be good. That would also allow you to probably add like so right now the F over, right now the feeds are like, they're at an F over D of 0.25 for a parabola. So that means they're like sitting just at where the parabola ends, you know, so like the dish comes up and the feed is like right in the middle. So if you space them a little further apart, and even probably now if we really wanted to, you could, you know, just like imagine putting a little bit more mesh above it. That wouldn't change the beam shape very much, but might give you a little bit more radiative isolation between, you know, across cylinders. It's still true that our biggest crosstalk is coming from, you know, down the cylinder, which is what you would expect. And that, you know, we can't do much about.
Yeah, okay, I was thinking that if it's crosstalk along the cylinder, wouldn't having the cylinders at different angles mean that that shows up in different directions on the sky, which means that sort of the even if it's in the side lobe of one cylinder, it wouldn't be for the other one, and
yeah,
disentangle what's in your main beam and what isn't in your main beam.
Yeah, and like the equivalent of that is kind of you're at different baseline spacings also, so you wouldn't expect it to show up at the same place on the sky. As you know, if you imagine one is straight and one is an angle, you know, they're different baseline spacings. So you'll also measure different modes that you wouldn't expect to be coupled unless it was physically coupled. Yeah. We accidentally, yeah.
Can't you just move them a bit further apart?
Not anymore. Yeah.
Okay.
Yeah. I'm gonna ask one question, Sigurd, and then probably we should close it. So you mentioned that the cosmological results that, or at least the forecasts you showed, are based on the 5-year survey. I don't know how much you can say, but should we expect a intermediate cosmological result with less than 5 years of data?
Something I forgot to highlight as much as I should have, our biggest problem isn't data in the can. So like a 3-year survey would be totally fine to get excellent cosmology results. We would, if we're not sitting on them right now because the analysis is hard. So we're making up most of our analysis as we go. The gain, we're getting close, but it's taken us 3 years to basically get to the point where we're able to say our gain is nearly where we want it, or maybe at where we want it, and that our beams are modeled well enough that we might actually be able to start removing some of these effects from the beam maps or from the maps. So like my guess is that, and I don't want to forecast this, but my guess is that if we were sitting at a place where our analysis was really great, we just do it on however much data we'd already taken. And so whether that was 4 years or 5 years, that's, we'd probably process the whole thing unless there was some period of time that was really bad. Also, we probably won't stop at 5 years. At minimum, the FRB is, CHIME FRB will want to keep going, obviously, because they don't integrate anything. They're just looking for sources. So we probably won't stop at 5 years anyway. And those, I should have said, those forecasts assumed that we were basically thermally limited, noise limited by our, that we had reached the point where all of our noise was thermal only and not systematics. And so the 5 years was that we averaged that down enough that our final result was actually cosmic variance limited. We're certainly not at the point right now where we are, reaching the thermal noise floor of our noise expectations either, for all of the reasons that all the calibration, all the stuff about calibration that's hard.
Right.
Yeah.